that. Okay, so let me remind you what we saw in the last class. We performed this quantization of bosonic string. This quantization, we performed this quantization in an elaborate manner using this phase-space quantization technique. But let's now remember the end result. The end result was as follows. The Hilbert space of our theory was made up of 2 into infinity times oscillators times functions in 26 functions of x or functions of p in d variables, where d is the dimensions we say. That was our Hilbert space. Okay. Now this Hilbert space was the Hilbert space of was too large Hilbert space, as we see from the fact that we have functions of d variables. The correct Hilbert space should have functions of d minus 1 variables. But okay, and the fact that this Hilbert space was too large was told to us by a constraint that we had to impose on this quantum theory. The constraint took the form of an operator equation that was obeyed on states. Okay, and that operator equation, well, there were 2 operator equations, one for left movers, one for right movers, and the operator equations were, so let's call this n tilde. And also alpha prime by 4 squared is equal to alpha prime by 2 2n minus 3. Okay, just remind you where all these terms came from. This term here was just the you see the constraint effectively was simply the Hamiltonian on the worldsheet of the string is equal to 0. Or more precisely, the Hamiltonian could be written as a sum of a Hamiltonian for left movers and Hamiltonian for right movers. Independently, the left moving Hamiltonian and right moving Hamiltonian have to be 0. Okay, so these are the two conditions: the left moving Hamiltonian and right moving Hamiltonian 0. Okay, so let's remember what all these contributions were. This mass squared term. So this mass squared was minus p squared. And was simply the contribution to the Hamiltonian from the kinetic term for the zeros. Okay? It's to say, this is the kind of Hamiltonian we got in particle mechanics, for the reason that we have same Lagrangian to the zero modes as we have for particle mechanics. Okay? The factor of 4 is the fact that we've divided the Hamiltonian up into left moving and right moving parts. But there is a factor of 2. Fine. Okay. The stuff on the right hand side is new. Okay? The stuff on the right hand side is new, and it corresponds to the contribution of the Hamiltonian from the oscillators. Remember that in both for the left movers and the right movers, we have a sequence of oscillators of frequency 1, 2, 3, 4 up to infinity. N and n tilde here are shorthand notation, which denotes the weighted occupation number of these oscillators. So let's write that down. N is equal to sum over little n, n. N tilde is equal to sum over n tilde, where n is the occupation number of the nth left moving oscillator. Similarly, n tilde is the occupation number of the nth right moving oscillator. Okay? So, this is just a standard Hamiltonian of a system of harmonic oscillators. So, omega, the frequency, times occupation number. A sum over all the oscillators. Okay? So, what we had in the end was a bunch of oscillators times functions of 26 variables and a constraint imposed on the system, the constraint being Hamiltonian 0, which gave us this equation. Okay, now what does this mean? What does this mean physically? You see, this part, this p mu, is implemented on wave functions by differential operators. Okay? So, when you if you try to write down a wave function, a wave equation, if you try to write down this constraint as a wave equation on states, you would get, if for a moment we concentrated on states with particular, that were eigenstates under these occupation numbers, what you would get from here would be two things. Firstly, since we've got the same thing here and here, by subtracting these two equations, we come to the conclusion that the only allowed states are those for which the left-moving occupation, this left-moving level number n, is equal to the right-moving level number n. Okay, so that's our first conclusion. N is equal to n tilde on allowed states. And the second conclusion is that when this constraint is satisfied, the wave function of our system, the wave function of the system in any particular state with a particular value n and n tilde is the Klein-Gordon equation. Is the Klein-Gordon equation for a particle of mass m squared is equal to, now let's get everything to this side, so 2 by alpha prime into 2n minus e minus 2 12, which is the same thing as 2 by alpha prime into 2n because this equation simply becomes p squared plus m squared is equal to 0 with this particular value for the mass, and that is the Klein-Gordon equation for a massive particle with that value of mass. Is this clear? Okay? So what can we conclude? What's the physical interpretation of this system? The physical interpretation of this system is clear. What we have is a bunch of many different particles. How many different particles? Well, the particles are in one-to-one correspondence with the occupation numbers of this infinite number of harmonic oscillators. Given any set of occupation numbers of left movers and occupation numbers of right movers, subject to this one constraint, these are the only allowed occupation numbers. Okay? We have a particle of a given mass. Okay? What is the mass of the particle? It's equal to 2n minus d minus 2 by 12 times 2 by alpha prime. And that particle moves freely in space. It obeys the Klein-Gordon equation with that mass. Okay? Different occupation numbers give you different particles, which typically have different masses. What is the largest mass of the system? At this level, there's no largest mass of the system. N can become as large as you want, because occupation numbers, harmonic oscillators, are not counted from above. Okay? So, we've got an infinite number of particles of arbitrarily high mass or fooling around with each other. Well, at the level that we've discussed things, these particles are free. So they're not interacting with each other. But of course, string theory is interesting because we can free ourselves of this free constraint and things will soon start interacting. Okay? So, the quantization that we perform in this intuitive manner has given us already an interesting result. Okay? What we've got is a system of particles, of free particles, an infinite number of them, of arbitrarily high mass, all of which obey the free Klein-Gordon equation. Is this clear? Questions or comments? Okay. Now, we've answered the question of what the highest mass is in the system. Now let's turn to the question of what is the lowest mass in the system. Okay? What's the lowest mass in the system? Well, we want the smallest value of n squared. Here, the smallest value of n squared occurs when n is equal to n tilde is equal to 0. None of the harmonic oscillators are occupied. In which case, we get m squared is equal to minus 2 by alpha prime d minus d minus 2 by 2. Okay. Now, the thing that's worrying about this formula is the minus. It's just a fact that the bosonic string, the string that's being quantized, includes in its spectrum a particle of negative mass. At least one particle of negative mass. Okay? Particles of negative mass have a name, they're called tachyons. Okay. Now, negative mass sometimes brings to mind, especially the word tachyons, sometimes brings to mind exotic phenomena like faster than light motion. This is all bunkum. You see, negative mass, in order to understand what it means for a particle to have negative mass, you should think of the mass as the second derivative of the potential for the particle, for the phi field, for the field described in the particle, about about the value of field equals 0. Okay. Generally speaking, I mean, if you've got a stable theory, if you're doing perturbation theory around a stable minimum, okay, then the second derivative is either 0 or in most cases positive. It tells you that remove your field a little bit away, it wants to roll back to phi equals 0. Okay? The positivity of the second derivative is the mass squared, as we said, and the positivity of that second derivative is the positivity of mass. However, suppose you were doing an expansion. You're trying to do an expansion in perturbation theory about a potential which curved the other way, which is negative second derivative. If you wrote down the Lagrangian of the particle, truncated quadratic order, you would write down the Lagrangian of the particle with formally negative mass squared. What is negative mass squared telling you therefore? What it's telling you is that the point about which you're writing down a perturbation theory in your Lagrangian is not a stable minimum. There's an unstable direction in which to move. You can see this clearly if you try to solve the equations of motion for a Klein-Gordon system with negative mass squared. You find that at low enough frequencies, low enough wave numbers, like wave numbers smaller than mass, or wave, whatever, inverse wavelength smaller than mass, you will find that the solutions don't oscillate in time, but exponentially grow and decay. Okay? Which is a characteristic of an unstable system. Okay. So, while there's nothing pathological, there's no faster than light travel, nothing theoretically pathological about negative mass squares, it does indicate that if you're trying to do a perturbation expansion of some sort of theory, you started about a particularly unfortunate point. It tells you that you've started about that point. If you want to deal with this, you should find the true minimum of the system if it exists. Move there, and then do your expansion about there. Then you have all positive masses, and you'll be able to do a usual perturbation theory with no intranet divergences. Okay? So, we've hit upon an unfortunate and undesirable feature immediately in our study of the Bosonic string. Now, namely, the fact that we've discovered that we've got at least one unstable direction in our perturbation theory. This theory, whatever it is, we've been unfortunate enough to expand this theory, whatever it is, we know what it is, about an unstable point. Now, this problem, the question of whether the bosonic string, the theory we are describing here, does have a good stable point about which to expand, or just some sick theory, with the maximum and the bottom to its potential, is a fascinating question, which has not yet been resolved, in my opinion, clearly one way or the other. Okay? However, so this theory that we've understood how to quantize in class so far has not proved useful for physics so far. It's just some formal thing. However, there is another system that is very closely related to this. A theory, a worldsheet theory is quantization, is very similar to the one we performed, which includes, in addition to bosonic fields on the worldsheet of the string, some fermionic fields. Okay? In that system, this problem goes away. Okay? So, all physics that is done with string theory and with perturbative string theory is done with the fermionic string. The string theory that does not have this fermionic. Okay? However, dealing with that string is technically complicated by the fact that you have to deal with fermions, the fact that you have to introduce notions of supersymmetry, because the string on the well, the action of the well shape, the string is supersymmetric and sort of unnatural to talk about that without giving you a little introduction to supersymmetry. Okay, so in any course of string theory, you're faced with these crossroads, and different times of teaching this course, I've chosen to go different ways. But this time we're going to go along the route of Bosonic. As we're going to say, look, believe me, that when you grow up a couple of months from now, or 3 months from now, we will tell you about the string that doesn't have this problem. So even though it's a problem and it means we can't do real physics with this system, allow me to forget about that fact and go on with the system. Because you will learn in a technically simpler setting, many lessons that will be useful, that you will be able to bodily carry over into the more complicated setting, where you have a string with fermions of the world sheet and you have no tachyons. Okay? So actually I've never taught the course this way, partly because when I was a student I found it very unsatisfying. But one should experiment in life, so this is the way we're going to teach it. Now we're going to go this way. Okay?
Regarding whether we have chosen the wrong vacuum in Bosonic string theory,
yes.
Can we really answer it without going into string field theory? I mean, from remaining within the realm of string quantum mechanics?
Well, you see, one way to try to answer this might be using renormalization group techniques for the world sheet. You know, the most, while string field theory is proved very useful in studying open string theory, tachyon condensation in the open string. It's not proved very useful so far with the study of tachyon condensation for closed strings. The techniques that proved useful there have been different techniques. Techniques that try to go off shell by using renormalization group flow techniques to world shape the string, which are purely first quantized techniques. Okay, so I would say that is, for instance, the Adams-Polchinski-Silverstein paper that described the decay of cones to flat space, use that technique. Now, I would say so that techniques are not barrier. There's no conceptual barrier for techniques. Yeah? I think first quantized string theory might well be enough. It's just that nobody's come up with a good way of addressing this question so far. It's very possible that the bosonic string is just itself, just by itself, a single theory. Okay? On the other hand, as we will see, we'll go with months studying this theory, and apart from the tachyon, we find no other problem. Somehow I find that it could be that it plays into the game in some way, but basically, nothing is not about it. Okay, good question. Other questions on it? Okay, so I'm going to ask your lead to suppress your discomfort with the fact that we're working about an unstable minimum, and let me continue for the next 2 or 3 months. And then we come back and hear this one. Okay, good. So that's fine. So we've got a lowest mass particle with just indicates instability. Okay, but let's look at the next particle. Okay, other problems will also be the next one. So let's set n is equal to n tilde equal to 1. This we can do, remember, because we got a harmonic oscillator with frequency 1. So we can excite 1 unit of that harmonic oscillator. Okay, then what do we get? Okay, so firstly let's count how many such objects we have. Well, we had d minus 2 options. Remember what we could do. What state is this? This is alpha I, and we call this minus 1 on 0. Alpha tilde j minus 1 on 0. Remember our notation? This minus 1 was the left of minuses were creation operators. 1, 2, 3, 4 label the frequency of the oscillator. Okay? So I'm acting on a vacuum with the creation of one creation operator frequency minus 1 on the left, of frequency 1 on the left, and one creation operator of frequency 1 on the right. Clearly this sets n equals 1 and n tilde equals 1. Clearly this is also the only way of getting n equals 1 and n tilde equals 1. Because you either excited two excitations of the harmonic oscillator frequency 1 or one excitation of the harmonic oscillator any other frequency, you would go about n equals 1. Okay? So, if we go to the next mass level, what is that mass? That m squared is equal to 2 minus d minus 2 over 12. We find that the number of such particles, the number of particles that we have here is 24 into 24. Because each of I and j run over 24. D minus 2 into d minus 2. Sorry. D minus 2 into d minus 2. Is each of I and j run over d minus 2 values. Okay? We've got so many components of the particle, so many fields for a particle of this mass. Now, there seems to be a more if you look at this answer, there seems to be a more serious problem with this answer than the problem of the instability of the vacuum. And this problem seems this problem that appears when you look at it is the following. Look, this particle, wherever it is, clearly transforms under space-time rotations because it has a vector index times another vector index. Okay? But the particle appears to be one of non-zero mass. We will come back to that in a moment. And now, the problem is the following. You see, it's a general property from group theory, from the study of the representations of the Poincare group, that massive particles transform in representations of SO d minus 1. Is this familiar to people? Basically what I'm saying is that when you look at the wave functions of a particle, you have both its momentum as well as its spin directions. Okay? But you can always go into a frame in which the momentum is 0. And in that frame, the part of the Lorentz group that is unbroken by this choice of frame is rotations. So rotations must be expressed. This particle must transform in some representation of this remaining unbroken rotation group, which is SOD minus 1. Okay, now how many of you are familiar with this Wigner theory of representations of the Poincare group? So only don't know. Oh, little bit. Okay, this is something I'm not going to teach it here. It would take too long, but it's something I strongly recommend that you learn about. Okay, representations of the Poincare. Okay, which tell you that in general, for a massive particle in these dimensions, it must transform in representations of SOD minus d minus 1. Okay, this is in 4 dimensions. That's familiar analog. The massive particles transform in representations of SO3. Okay, now this seems like a problem because these states here clearly do not transform in representations of SOD minus 1. Okay, so let me work the problem by suppressing the fact that they're both left movers and right movers. Okay, let me think of just the left movers for a while. Okay, you've got objects. You've got 24 different states, d minus 2 different states, each of which clearly, and these states clearly transform in a vectorial representation of SOD minus 2. Okay? Now you can ask, is there any d minus 2 dimensional representation of SOD minus 1 such that it includes all the states transform as vector of SOD minus 2 and there are no other states? And clearly the answer is no. The nearest thing to this kind of representation is a vector of SOD minus 1, which in addition to these d minus 2 states which transform as vector of SOD minus 2 include a state which would be a singlet of SOD minus 2 but is needed to complete the multiplet into full vector of SOD minus 1. Is this clear? Good. got some big SO. Let's say SO d minus 1. Okay? And let's break this up into one row and one column. And so this is 1, and this is d minus 2. D minus 2. And this is 1. Okay. Now, let's look at a familiar representation of x of d minus 1, namely the Victorian representation. How many elements does this have? It has d minus 1 elements. Okay. These d minus 1 elements can be thought of as this column. Of these d minus 1 elements, with this choice of breaking x of d minus 1 up into x of d minus 2 other stuff, these guys transform as a vector of x of d minus 2. Okay? But there's one more element in the representation that under x of d minus 2 is a singlet. Is this clear? So there is a representation of x of d minus 1 that includes that when you break it up into representations of x over d minus 2 includes the vectorial representation. But but this representation has exactly one more element. Okay? And of course, if you think about it, you will convince yourself that there is no representation of x of d minus 1 that has 24 elements, that has d minus 2 elements, all of which transform in a vectorial representation of x of d minus 1, d minus 2. That's impossible, right? It's breaking the symmetry between the d minus 2 dimensions and the remaining one dimension. Okay? So, this confusion is not changed when you tensor this thing with something else from the right hand side. So we conclude that the states that we've got at level 1 do not transform in representations of S of d minus 1. Now, this is a direct contradiction with some general theorem about how particles in d minus 1 dimensions, in a Lorentz invariant theory, d minus 1, in d space-time dimensions should behave. And so it looks like a contradiction that's more serious than instability. It looks just like you're getting something wrong. And you might ask, is there any way around it? Now, there is a way around it. And the way is interesting. You see, everything I said about particles transforming representations of S of d minus 1 is true for massive particles. But it's not true for massless particles. You see, the intuition is that while it's always possible to get into the rest frame of a massive particle, that's not possible for a massless particle. The best you can do is use Lorentz transformations to make sure that the momentum of the massless particle is in one particular direction. Let's say the d minus 1th direction. Okay? Now, once you make this choice of frame, the rotational part of the symmetry that you have left is x of d minus 2 rather than x of d minus 1. Is this clear? Because time is special and the x direction is special, or d minus 1 direction is special. The other directions are all equivalent. Okay? So, and this intuition turns out to be correct. Wiener's general analysis tells you that massless particles, fields for massless particles, transform in representations of x of d minus 2 rather than x of d minus 1. Okay. So, perhaps this is what's going on. Okay? Perhaps what's going on is that this particle at level 1 is massless. If that were true, all of this would be consistent. Okay? Now, when would that be true? Well, it would only be true if 24 was equal to d minus 2. So it would only be true if d was equal to 26. Okay? So, we tentatively move on here. You say, well, let us, this whole thing doesn't seem to make any sense unless, let us level 1. We have massless particles. And perhaps we can be, we can respect Lorentz invariance and Wiener's theorem. Okay, but you might think now we're on a very slippery slope. Because you might think, well, the way we've done things, we always have things or manifesting representations of x of d minus 2, but you're going to have a hard time building things up in representations of x of d minus 1. You wiggled out of it, at level 1 by saying this guy is massless, but unfortunately, if you're massless at level 1, you can't be massless at level 2. So what are you going to do at the next level? So let's see. So is the question clear? So let's work with level 2. So now we're working with n equals to n tilde. Now what? Firstly, let's list all the states that we have here. Okay? I'm going to just list the left movers, and we're going to tensor this with whatever we have with the same thing for the right movers. Okay? All the group theory, everything works sector by sector. So let's just list it out. But firstly, we have alpha minus 1i, alpha minus 1j acting on the back. Is there anything else we have left? Very good. We also have alpha I minus 2 acting. Now you might think, well, we've got everything in representations of x to the minus 2. It would be a miracle if it transforms into representation of x over the minus 1. But let's see if this miracle is indeed true. So let's look at a particular representation of x over the minus 1. Namely, the symmetric traceless representation of x over the minus 1. Okay? What is that? Its elements are matrices, are d minus 1 times d minus 1 dimensional matrices that are symmetric and traceless. Okay? This is unlike the representation we looked at before, which is just a column. It's a bigger representation. It's a matrix. Okay, and let's take this representation and break it out into representations of x over d minus 2. Okay. Now, let's see. We've got a matrix here. So, this one, so once again we take this matrix and break it up into 1 and d minus 2 and 1 and d minus 2. Okay, so this is d minus 2 times d minus 2 matrix. Is this clear? Okay, now clearly something that was symmetric in the full space remains symmetric in this space. So this thing here is a symmetric matrix of S of d minus 2. This is not traceless, not necessarily traceless. The trace notation of the full space tells you that this element plus the trace is 0. Okay? But by agreeing to take, so the trace is not 0, but it's related to what's happening here. So it's not an independent degree of freedom. Okay? So, in counting representations, we can remove the trace if we agree to count this element here. Okay, so the question I'm asking now is, if you have the symmetric traceless representation of x over d minus 1, what representations of x over d minus 2 does it break out? So what do we have? Well, we've got the symmetric tensor of x over d minus 2. Let's remove its trace. So that's the trace, the sublinear combination of the trace in this guy is a scalar. Plus, we've got these rows and these columns. Because the original matrix was symmetric, they equal to each other, so we count only one of them. So the net conclusion is that what we've got is a symmetric traceless representation, a scalar, and a vector. Okay? So what we concluded that sim traceless of d minus 1 is equal to sim traceless, or decomposes into string traceless of d minus 2 plus vector of d minus 2 plus scalar of d minus 2. This is clear. Look, now I'm unhappy. Okay, if you want to convince yourself by counting components, that the component counting matches. The formula you have to verify is that d minus 1 into d by 2 minus 1, so that traceless tensor d minus 1 is equal to d minus 2 times d minus 1 by 2 plus d plus 1 which I can't do in real time, but presumably is true. Sorry, and this is this plus d minus 2 plus 1. And then maybe I can. Okay, we can take this out common. O. That's right. That's it. What? Sorry. Let's get this straight. Right. So that's the trace. Okay. This is d minus 2 to d minus 1 by 2 plus a vector, so that's d minus 2 plus a scalar. Okay. Let's just check this, right? So since we start getting on it. Thank you. There's also a minus 1 here. And then is it right? Okay, let's just verify this. So what is this? So this is d squared minus 2d minus 2 over 2. And what is this? This is d squared minus 3d plus 1 plus 2d minus 4. Oh, this is plus 2. Over 2. This is d squared minus d. Thank you. So it's correct. Okay, sorry. Okay. Now, why have I said all of this? I've said all of this because what we have here is precisely this combination. You see, under SO d minus 2, we have precisely a vector and a symmetric tensor, which can be thought of as a symmetric trace, is tensor plus the trace. So the representation content that we have under SO d minus 2 is precisely of the sort that nicely combines into an SO d minus 1 representation. Since this works for left movers, it also works for right movers, and therefore it works for the tensor product. Okay, so at level 2 there was a potential problem, which actually is not a problem. The group theory is okay. Now, although we're not going to try to check this in class, if you guys wanted, I could give you assignments for this course. There's a way to formally check. Okay, so certainly I would advise every one of you to check this at level 3. Check at level 3 to the same levels. Okay. There are ways to formally check that this continues to happen at every level. Okay? So, all you need to do is one cheat. That one cheat is not actually cheat because, well, it fixes something you didn't know. It fixes what dimension you were working. Okay? But once you've done the one fix, everything else works. Okay? So the theory that we're working with is consistent with Lorentz integrals and group theory, representation theory, but only if we were working in D equals 26. And the reason we needed that D equals 26 from this point of view was for this one little thing that is states at one particular level, namely the first level, would violate Lorentz invariance unless it were true that they were masses. Okay. Now, you might ask, where in our quantization procedure, was logically necessary to ask for D equals 26. See, it's a little unsatisfying to follow a procedure which you think is okay, and then fine-tune some parameters in that procedure, not on the basis of logic, but on the basis of the answer making sense. It's a little unsatisfying. And, we will answer this question in the next 4 or 5 lectures. But in order to answer that question, we have to do a a slightly more serious job of the quantization of this theory. Okay? But let me give you a very rough answer to that question immediately. You remember that in this procedure of quantizing the string, the place we got this -1/12 from included a physical assumption. That was the assumption of conformal invariance of the word sheet of the string. That was the thing that uniquely fixed. That was the thing that uniquely fixed 1 plus 2 plus 3 plus 4 equals -1/12. Okay, now the conformal invariance that we wanted was a consequence of symmetries that we wanted to inform, that we wanted to have, wanted to keep true in our quantization. These symmetries were reparametrization invariance on the word sheet of the string and while invariance on the word sheet of the string. Okay, so while it is true that these two symmetries are only maintained provided that d is equal, provided that 1 plus 2 plus 3 plus 4 is equal to -1/12. This turns out not to be the only condition. If you do a more serious job of analyzing the path and textbook of this theory and asking the while invariance and the diffeomorphism invariance and the word sheet of the string remain symmetries of the theory, you require, in addition to this fact, you require that d is equal to 26. How that comes about, we will see in the next few lectures after we understand the conformal. Okay, but I just wanted to assure you at this point that there is a systematic procedure. That if you do things more seriously, you will see where the procedure things break down, unless d is equal to 26. So d equals 26 has another more satisfying derivation, which we will get to rather soon. Okay, but once you know that, we're happy with our quantization of the string. Okay, and now let's immediately look to see what the consequence, what the result that we got is. So we've got this one unstable particle which we decided not to bother with. But here in addition we've got some massless current. That's nice. Massless particles are always interesting. They're always really interesting physics. So let's understand exactly what the massless particles we have. Okay. So the massless particles, remember, were in the 24 times 24 of SO24. The vector times the vector of SO24. Now if you try to take this vector times vector and decompose it into irreducible representations, can somebody do that for me? Can somebody decompose vector times vector into irreducible representations of any SO group? Very good. Very good. Symmetric tensor, traceless symmetric tensor, antisymmetric tensor, and the trace. Okay, so what we get here is under SO24 we've got a traceless symmetric tensor, an antisymmetric tensor, and a trace. The point is, okay, these two, the fields associated with the antisymmetric tensor has a name, it's called BUU, and we'll encounter it in many guises as we go along in our study of string theory. The field associated with the trace also has a name, it's an important field, it's called the dilaton. We'll encounter it, you'll know as we go along in our study of string theory. But the thing I want to focus on at the moment is this traceless symmetric tensor. Okay, listen. The traceless symmetric tensor is very interesting. It's very interesting because if you take Einstein gravity and linearize it, okay, linearize it, look at small fluctuations, and you ask in what representation physical excitations, physical excitations of the gravitons transform in 3 dimensions. The answer to that question is in the traceless symmetric tensor representation of SOD minus 2. Okay? So the fact that we've got a symmetric tensor floating around the place, is a tantalizing indication that we may be a massless symmetric tensor of different. That's really crucial. Okay? Is a tantalizing indication that we may be dealing with a theory of gravity. Okay, now it may be more than an indication. There are various claims whose levels of, how much you should believe these claims up to the reader. But there are various claims, the most systematic of them being by Feynman in this book that he wrote called Lectures on Gravitation. Okay? There are various claims by various people, most systematically by Feynman, that if you want to study that any theory that includes massless symmetric fields and is a consistent unitary makes up a consistent unitary quantum field theory, okay, must be a theory of gravity. And what do I mean by theory of gravity? In the sense that it must implement diffeomorphism invariance. Okay. Let us, for our generalized purposes, talk about any theory that is invariant, that implements diffeomorphism invariance as a theory of gravity. Okay. So the various claims floating around that say that if you have the only way to make a consistent quantum theory of massless fields in massless tensor fields, okay, is by making it a theory of gravity. Let me give you a 1-minute introduction to the idea behind these claims. The idea behind these claims is very similar to the idea behind, a similar likely to be true statement about vector fields. Suppose you take a theory, a quantum field theory involving vector fields. You've got a theory involving mu. Okay? And you canonically quantize it. When you do the canonical quantization in the vector invariant fashion, you get a mu dagger. You get you get okay, and you define a mu dagger, a mu as the object that anti-Higgs vacuum. So that's creation operator. You get the canonical commutation relation a mu dagger equals eta mu. Okay, what else could it have been? It looks like Lorentz. Now, when mu and mu are spatial indices, this is a standard commutation relation for harmonic oscillator. When mu and mu is time, these are the wrong commutation relations for harmonic oscillator. Okay, it's for time this becomes annihilation of creation is equal to 1, rather than creation with annihilation is equal to 1. Okay, and that leads to all kinds of trouble. Basically, conflict with unitarity, with boundedness of the energy spectrum. Okay, so you might think that it's pretty hard to build, because of this problem, you might think that it's pretty hard to build a consistent quantum theory with massless electromagnetic fields, with massless vector fields. And the fix to this turns out to be, and it is hard to build a theory, the theory just based on the Lagrangian del a mu, the whole thing squared, makes no sense. But there is a fix to this, and that is introduce a gauge symmetry into the problem, which allows you to, which is so large that it allows you to eliminate the time-like degree of freedom. This is the usual Maxwell gauge symmetry. If you eliminate the time-like degree of freedom, then you have only states with positive norm and you have no trouble. Okay? The problem is even more serious when you look at the theory of gravity. When you look at the theory based on symmetric tensors. Because if you look at the theory based on symmetric tensors, you've got T plus A mu A alpha beta, and then this has got to be A mu eta mu alpha eta mu beta plus symmetric. What? One of them should be a dagger. One of them should be a dagger. Okay? And once again, these are perfectly sensible canonical commutation relations where everything is space. or actually in this case when both are time. Because then there are two minus signs. But when you have one space and one time, you have trouble. Okay, you get the wrong sign commutation relations. Okay, and in order to cure that, you need a gauge invariance once again. Something that will allow you to eliminate the bad degrees of freedom. And basically, these arguments that try to show that the only way to make sense of a massless blah 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 theory try to argue that the only consistent gauge invariance in this theory is diffeomorphisms, which is a maximum symmetry. Okay. Now, I don't want to go on with these general arguments very much, because who knows whether they're true. Such general arguments or make lots of assumptions, and assumptions might be violated and so on. However, the basic idea seems plausible. It seems hard to make. Certainly, there are no examples of theories, interaction theories, interesting theories with symmetric fields that are massless and that don't have diffeomorphism invariance, therefore not theories of gravity. Okay, so this is the fact that the bosonic string has massless symmetric particles is a stronger indication than you may first find out. Okay, that it is a theory. Okay, however, of course, we will see this in much more detail than these words. We will see as we go down in our study that what we're building is a theory of gravity.
Supposing, okay, this is probably support results. Supposing it turns out that whatever we see as quantum mechanics, it turns out to be a very special piece of a classical theory. Then
doesn't that violate Bell's inequalities?
Probably going to do that.
Yeah, I think that's. Well, I don't know that much about it either, but it's not easy to reproduce quantum mechanics by any classical theory. Right? There were these sharp inequalities that were tested experimentally. So that, in any classical theory, you get something less than this. In the quantum theory, you get something that violates that bound and test it. It's not,
I'm asking this because most of the time, the kind of actions we deal with, they turn out to be very classical things.
Yes. But they're quantized.
Somehow it seems to work.
What seems to work?
The classical actions, and after we eliminate the zero modes.
Well, any quantum system which is weakly enough coupled with H cross small enough is approximately classical. And so has classical limits. So that's true, but it doesn't stop, spoil the fact that it is quantum. It's just how weird quantum physics is from classical point of view. It's really well emphasized by these lectures that Feynman gave. Feynman lectures on physics, the first 3 chapters of volume 3, in which he tried to track down which hole the bullet was. It's, maybe if you make things weird enough, you can make them. It's not easy. Quantum mechanics is very different from classical mechanics in rather important ways. Also, as those lectures emphasize, it's never consistent in the quantum theory to have half of the word quantum and the other half classical. That's never consistent. Can somebody tell? Okay, we'll take a 2-minute break just to answer this question. Can somebody give me an argument? A simple physical argument that tells you that's not, world would be inconsistent if there was anything classical. Okay, let's be clear. If gravity was classical, and everything else was quantum, could this be consistent?
Would make sense. At all length scales, suddenly, there should be, how can the theory be suddenly be different in certain length scale?
Okay, but we want to sharpen up.
If it has to be classical at one length scale, it has to be classical at all scales.
Why?
Because uncertainty.
The uncertainty principle will be finite. Good, can you sharpen that?
Basically, you can make gravitational measurements which can measure.
That's exactly right. Let me just say that more, in the context of given experiment. So experiment Feynman told us about, those lectures. If you remember, he was dealing with double slit experiment. Okay? He was dealing with double slit experiment and he was throwing, electrons at the slit. And was finding that if he had just one of these slits, he got a curve like this. Another slit, he got a curve like this. Should the same size and overlapping in the center. What? Okay. But if you have both of them open, you got a curve like this, like of interference. And this, he was very puzzled by it. He was saying, well, presumably electrons either go through that slit or go through that slit. Presumably the electrons that go through this slit don't know or care whether this one's open or not. So how can it be that what you get when both slits are open is different from the sum of what you get when each one is open? And then he tried to track it down, with an experiment. He said, well, let me do the following. Let me keep both slits open, but see which one the electrons go through. If I can do that, it must be that I get the sum of those that go through the first plus those that go through the second. Okay? So how do you try to do the scene? Try to do that by taking a photon down, and shooting these photons at the electron. And then measuring the scattered photon. From difference in direction from which the photons came, you could see which one the electron went. Okay. But then he had a problem. He had a problem because if he chose the photons to be too small in wavelength, then the kick they carried was so strong that it could take an electron that was headed there and make it head here. It was strong enough to kick the electrons enough to smear out the interference pattern. On the other hand, if he made the photons too large, because of the big wavelength of the photons, you couldn't detect the direction of the measurement was not sensitive enough to say whether the photon was coming from being scattered from here or from there. And it was precisely at this point. If you try to make the photons large enough so that you didn't kick the electrons enough to smear off the interference pattern, you made them so large that you couldn't detect which slit the electron came through. So as a function of photon size, as you took the photons very small, you would be able to see the electrons, you would be able to see which slit the electrons came through, and you would find this interference pattern, some of these two. Then you make the photons larger and larger and larger and larger. Your resolution of where they came through becomes lower and lower and lower, and the pattern becomes nearer and nearer to this. Okay? Quantum mechanics lives on the edge of not making sense. It's very finely tuned theory. Okay? Now, suppose these photons have been classical. Then you see, you can make the photons very small and yet very small energy. Making them very small, you'll be able to detect which slit the electron came through. Making them very small energy, you would kick the electron almost not at all. So had you had quantum electrons interacting with classical photons, the theory wouldn't have made sense. Or at least would have been greatly different. Okay? Everything as your photons is true about gravitons. It just wouldn't work in quantum mechanics if you had some particles of classical and others of quantum. Precisely because you would buy the concept. Okay, so that was a philosophical aside. But good. The need for quantum gravity, but good. Okay, any other questions or comments before? Okay, so we've completed our little mini round one. We've completed a little quantization of the bosonic string, and we've seen the result. We've seen that we get master spin 2 particles, so presumably that counts. Okay, now we're going to go back and do things more systematically through a more detailed study of the kind of quantum theory influence in the world shape of the string that they conformity theory. So that's the plan for the next few lectures. Relatively thorough study of conformity theory. Okay, so let's go. Our study of conformity theory, and much of what we do in this course, which is quantum mechanical, will be done following Kolchinsky. Okay, so now from now on, I'm following Kolchinsky chapter 2, but perhaps not in the order that Kolchinsky chapter 2 is written, which I find a very convoluted. I think that's said in the camera. Okay. Okay. So the study of conformity theory, but much of the other quantum mechanics we do, will be using the path integral formulation of quantum mechanics. Okay, so partly as a warm up in using path integrals, but largely because we need the results. And now we can use path integrals to derive two or three famous results in quantum and they have analog classical field theories relating to symmetries. Okay, so the first thing I'm going to do is to derive the normal theorem. Okay, using the path integral from quantum mechanics or quantum field theories. Okay, so firstly, what is the path integral formulation? Well, you know, there's some partition function which is defined by an integral over fields and an exponential of I times some action, which is function. In quantum mechanics, those fields are functions of time only. In quantum field theory, those fields are functions of both time and a certain number of space dimensions. We're working in 1 plus 1 dimensions, so our fields will generally be functions of time and one space dimension. Okay. Now, interesting objects that you compute in quantum field theory and will be of great interest to us as we move on in the course, as you will see, are correlation functions. That is, objects of the following form. Okay, I'll tell you what these. First thing, let's define terms. X1 and x1 to xn are positions on the field theory space, which in this case is two-dimensional. Okay, I often use the symbol x to denote both the space and time position. It's x mean. Okay, now what are these O's? These O's are any local function of the field theory. Okay, so. O's are called operators, or local operators, and for instance, if the fields of the theory, as will be the case in the Bosonic string that we studied, are x mu or sigma 1 or sigma 2 or sigma tau, then you can make many local operators out of x mu. For instance, you can make the operator, well, x mu itself is an operator. You could make operators like del alpha of x mu at a given point in space, or you could take even part I k x at that same point in space, and so any functions of the x's that depend only on the value of the x at the particular point of interest and is immediately. Okay, so depends on the fields and derivatives of the fields at that point. Okay. So, as we will see as we go along, the combination of correlation functions for the action of the wedge of the string will be very important to us. Okay, so, these correlation functions are often defined after dividing by the partial functions. So now we're going to try now to something that I will often do in this course is work interchangeably with the Lorentzian and Euclidean formulations of quantum. Okay, so you might find me switching this is to minus s, in which case I'm working with the Euclidean action. Okay, when we actually move from when we actually need it for physics, that is, when we actually use Euclidean action for the worldsheet of the string in order to do a calculation, we justify this very carefully. Why the physical calculation that we want to do, which is a Lorentzian calculation, can equally be well done in a Euclidean setting. But until we get there, for formal purposes, the manipulations I will do will sometimes be Lorentzian, sometimes be Euclidean space, sometimes it won't matter, sometimes it will. Okay. So, for manipulation purposes, for formal purposes, I would often work in the Euclidean theory. In order to answer a physical question, we must be very careful about what we're doing, and we'll always be careful. Okay, but the next few lectures, the next 5 lectures or so, will be about conformal field theory. We'll be doing no string theory. We'll look at the application of this to the study of string theory only 5 lectures from now. Okay, so it will be hard in the next 5 lectures to answer questions like where will this go in string theory, or why is this the correct thing to do from the point of view of string theory, because we'll get to that only 5 lectures. Okay, so this is just formal exercise for studying the kind of quantum field theory at the moment. Of course, the reason we're studying this is this kind of quantum field theory that appears in coefficients. Okay, then. So we will be interested in these objects in quantum field theory. Now, I want to derive certain well-known, but anyway, just set notation in case you haven't seen this way of deriving it, and well, it'll be very useful. Properties of these correlation functions implied by the existence of symmetry. Implied by the existence of symmetry in the theory. Okay, so firstly, I have to define for you what is symmetry. So consider the partition function here that takes this form. Now, suppose you can find a variable change x to some function of x prime. Okay? Such that under the variable change, the path integral takes the same functional form when expressed in terms of x prime as it took when expressed in terms of x. Now, z, if you just make this variable change into this integral, it turns into the integral dx prime exponential of minus s. I emphasize that what I'm talking about here is functional form, because all I've done is a variable change. The variable change can't change the value of an integral. Of course, whether you make a variable change by symmetry or by anything else, the value of the integral hasn't changed. But most variable changes will change the form of the integral. Okay? If you can find symmetry variable changes that don't change the form of the integral, it's the same function, the integral is unchanged. Okay? Such a variable change is called a symmetry of a particle. Now, why are symmetries interesting? Symmetries are interesting because they're associated with conservation laws and related to water. Okay? So let's try to understand. So, firstly, we will be interested mainly in continuous symmetries. So symmetries that depend on one parameter, that when this parameter is taken to 0, it will take you to the identity transformation. Okay? So for such symmetries, we can take the value of this parameter to be very small. So infinitesimally, our variable change takes the form x is equal to x prime plus epsilon times some g. Okay? So in particular, it's true that if we make this variable change,
just a second. Then when you wrote z as z in terms of x prime,
yeah,
you have not imposed any symmetry yet.
Well, there is a symmetry if there exists a variable change, such that if I make a variable change, the integral does not change. Yeah. Okay? That's what it means for there to be symmetrical. Okay? Given an arbitrary path integral, there may or may not exist symmetry. Because variable change of identity, something is equal to itself, always exists, but that's true. We want more. Okay? So we're looking at symmetries that have infinitesimal versions. So that such a variable change takes that form. Okay. Now, what consequence can we draw from the path integral using the fact? Please.
So if you have some function Jacobian, we should absorb it in the explanation.
Yes. So now this is symmetry after you've taken care of the Jacobian. This result is true. Okay. So once you have re-expressed everything in terms of dx prime, what you have here should be e to the power minus x. There are many ways in which it could happen. Could be that the Jacobian is 1 and the action is 0. Could be that the Jacobian is not trivial, the action is not trivial, changes, but the two cancel. Both forms are interesting and See, in quantum mechanics, all that is important is the path integral. The action separately, measure separately are not distinguishable. Okay, good. So now let's move on. So let's make an infinitesimal variable change of this form. If our action was, if our theory was, if we have a symmetry, then making this variable change, we get the same, we get the same partition function in terms of x prime. But now, okay, that hasn't taught us very much yet. But now we will do the following. Let's take this epsilon, which was a constant in order for this thing to be a symmetry, and make it a function of field theory coordinates. Okay? So let's perform the variable change. X is equal to x prime plus epsilon of, let's call it sigma alpha, g of x. And examine what happens to the path integral under this variable change. So what do we get? We know that if epsilon is constant, making the variable change simply gives us dx prime exponential of I times s of x prime. Okay, let me do the argument will always be clean space, so with fewer i's. Okay, e to the power minus s of x prime. Okay, this would be true if epsilon was constant. When epsilon is not a constant, because that is not necessarily symmetry of the action, we will get a change, but that change must be proportional to a derivative of epsilon. To reduce to the fact that when epsilon was a constant, we got no change. So, the most general thing must be del alpha epsilon and some function j alpha of x. This is it. Of course, you might ask, what if it has two derivatives? A function which is two derivatives of epsilon? And the answer is, well, if it has two derivatives, you can by integrating by parts transform out the derivatives instead. There must have at least one derivative. No claim that it has one exactly. Okay? You might also ask, well, why is this exponentiated? Why not in the numerator? Why not keep it downstairs? The answer is the first order in epsilon, which is where we're working, is no difference. Yeah, you can put things wherever you want. Okay? Good. So, this is what we got upon making the variable change in the action, in the partition function. But, of course, since it's a variable change, the value of the partition function hasn't changed. Okay? So this is the same thing as integral dx exponential of minus s of x, the original expression for the partition function. These two are as expressions equal. Now, let me make a change of dummy variables and call x prime equals x. And then subtract these two expressions. So we get the equation dx exponential of minus x minus s of x, and then we have a 1, let's expand this, leading order of epsilon. So we have 1 plus this business. So the one term, the term that was 1 cancels when you do the subtraction. That business survives. So, times integral del alpha epsilon j alpha of x is equal to 0. This is true for any function that we choose for epsilon, and therefore we conclude that the expectation value, now let's integrate this by parts. So let's integrate this by parts. So we get epsilon here, del alpha here, with a minus sign here, okay? Okay? We can choose epsilon to be anything we want, a delta function in particular. That tells us that the expectation value of del alpha j alpha equals 0. Okay? So we've reached our first conclusion. Our first conclusion is that every time we have a symmetry inside the path integral, that implies the existence of conserved charge. We've not fully proved that yet. We've only seen that it implies the existence of a charge whose that has a come to the expectation value vanishes. Whose expectation value of divergence vanishes. Of course, we want more, and we'll soon see that.
But is this observation just on shell or is it paradoxical?
No, it's just on shell. I mean, we'll see exactly how. In the quantum theory, the classical analog of the statement certainly is not valid if you violate the equations. Okay? And we'll see exactly how on shell the statement is. Okay, now this is an interesting statement, but as we said, the thing that we are often really interested in is expectation values of various operators. So the thing that would be more useful to have is a statement about what del alpha j alpha times O1 On gives. So what is this? That would be the more interesting statement. Okay, now how do we answer this question? Well, let's try the same manipulation as we did above, but by inserting some operators into the problem. Okay, so suppose we start with we take Z, which is